And as I pointed out, you can think about this as just a big multinomial. There would be 2 to the d categories in this multinomial. So for example, the first category, imagine I take a person at random. Right? A multinomial is like rolling a die. You roll a die with 6 possibilities. In this case, I take a random person, I don't get a 1 to a 6 that's going to die, I get a vector. And it can take values 0 to 0, 0 to 1, and there's 2 to the possible things. And we can even make a list now. Once I have n people, small n people, I can count how many fall into this category, this category, this category. So it would be a list of counts of length n equals 2b. And I can just think of that as a multinomial, and then draws from some probability vector plot. So for example, in the case d equals to 2, each outcome takes one of 4 forms, 2 to the 2 forms. Probability pi 1, pi 2, pi 3, pi 4. If you wanted to, you could just do multinomial estimation. You just estimate these 4 parameters. The problem with that is recovering conditional independence relations between the coordinates is not so easy in that parameterization. So we introduced the law of linear parameterization, which goes back to the x, which is a vector again. And this is a probability function, right? So that means it's the log of the probability that the first random coordinate takes this value, like could be a 0 or 1, and the second one and the third one. It's a probability function. And we said we could always re-express any multinomial in this form. It's a one-to-one relationship. It's some constant plus linear terms, quadratic terms, and so on. That's just called the law of linear parameterization. Come on, we can always go back and forth in principle from the multinomial representation to the law of linear representation. And what we saw was the nice thing about the law of linear representation is once I write this out and some of the terms are 0, like in any regression problem, some of the betas might be 0, we can check this rule that if the pair jk never appears together, if any time j and k appear together, that term is zeroed out, that implies a xj and xk are independent. That's our conditional independence. Or in the graph, there's no edge in J. So that's the link between the log linear representation and the graphical model, which is much clearer than what you try to do with the multinomial representation. So think of it again as you put some data into R, you fit the model, it's going to give you a bunch of betas, maybe you test some of them and set them equal to 0, or maybe we do a sparse estimate, we'll talk about that in a minute, which automatically makes some 0. Then you notice 3 and 4 never appear together in your model. Therefore, when you draw the graph, you need no edge between the two. So that's the path from the data to the final graph that you draw. We'll do a simple example. However, right at the end, we started to notice there's a little bit more information in the log linear representation than just the graph, or just the conditional independence relation. So let's look at the case again of 2 variables. Log of p of x, here's the saturated model, meaning I've put in everything. The graph, if it really looked like this, and when I put the term there, I mean that's like if I put a beta 1 there, I mean it's not 0 by including the formula. So that's not a very interesting graph, but with 2 variables that aren't the graphs which are interesting. But it's the fully connected graph. And suppose I find out that the true values of beta 1 and beta 2 are 0. What does that mean? Suppose I tell you that the probability, let's write it more explicitly. This is the probability x1 takes the value of x1, x2 takes the value of x2 is equal to beta 0 plus beta 1 to x1, x2. Is x1 conditionally independent of x2? No, we can't conclude that because 1, 2 appear together. So if you're drawing the graph, you do this. What's happened, though, by drawing these? That implies some constraint on the probabilities. It's just a constraint you can't represent with conditional independence graph. It's fine. But that raises the question of which models exactly are representing these conditional independence constraints and nothing else, versus which models are representing other features of the distribution. And so the distinction we make is this. If we take all log linear models, these are log linear models. This is going to be what's called the hierarchical models. Now, for those of you who are familiar with hierarchical Bayesian models, this is a totally different meaning, usage of the same word, so don't get it confused. It's unfortunate that we use the same phrase. This is a subset of the set of all log linear models. And then there's a smaller one. This is even more confusing terminology. They're called graphical log linear models. It's kind of confusing because all log linear models are representing graphs in some sense. They're all graphical models, but there's some log linear models that are called graphical log linear models. So what are these classes that I'm talking about? Hierarchical log linear model is simply a log linear model that follows the following convention. That if I set something equal to 0, so here I've set beta 1 equal to 0, then every higher order term must also be 0. That contains that index. So if I set beta 1 equal to 0, then I must set any other beta term with a 1 in it equal to 0. That's the definition of a hierarchical model. So in other words, this is a non-hierarchical model. Doesn't mean there's anything wrong with it. Some books will give you the impression that there's something wrong if you have a non-hierarchical model. There's nothing wrong with it. Nature can make up whatever probabilities it wants to. But it's a matter of definition. And a more interesting one will be to consider 3 variables. So let's consider 3 variables so we can get a clearer picture here. So log p let's do a few examples, and I'm going to ask you, is this model hierarchical or not? Just make sure where it's got this. So, if I X out this term and this term, is that a hierarchical model? Remember, the presence of the term means that that beta is not 0. So the zeros, I'm saying that beta 1, 2 is 0, beta 1, 2, 3 is 0. Is that hierarchical? Yes, it is. We haven't violated it. What if I zero out this one but leave this one? That's non-hierarchical because I've set 1, 2 equal to 0, but I have a term with 1, 2 that's not 0. So I have a bigger term that's not 0. Is that clear now? It's just anytime we set a beta A equals to 0, you need to require that beta sub B equals to 0 if A is a subset of B. That's the definition of a hierarchical. So models can be hierarchical or non-hierarchical. Most software restricts itself to hierarchical models. That's not always the case, but I think most programs do. Why? There's a couple reasons. Well, when you're doing model search, you're searching through models, you restrict yourself to hierarchical models, there's fewer of them. It's a restriction. It makes things a bit simpler. For example, when you do forward stepwise methods, and you start adding in terms into the model, you know that if I zero out beta 1, then when I start to add higher order interactions, I don't have to consider anything with a 1 in. So it makes your life simpler. However, we don't have any guarantee that the true model is hierarchical. So that's an assumption of convenience, but there's no reason to think that nature only generates hierarchical models. It's just a definition. There are some people who say, as a matter of principle, if I'm going to set this non-zero, then I should keep all the lower order interactions within the model. In other words, you would force it to be hierarchical. And some people think it's just not possible to interpret the model otherwise. I don't quite get that, but that's what some people insist on. That type of attitude, though, doesn't lead to errors, because if I see this as non-zero and I force all the lower order terms in, if this happens to be 0, that's fine. The beta hat will just get close to 0. So I'm just kind of over-parameterizing the model. I'm being less parsimonious than I need to be. So maybe it's not such a horrible mistake. But it is a distinction that people make, this hierarchical versus non-hierarchical, and it's somewhat arbitrary, but it's just think of it as a definition. However, the one that's a little bit more meaningful is this graphical model. And what it means, a model is graphical. Let me just say it. There's a formal definition in the notes. Let me just say it works. If I write down a model and say, could I add any other variables without changing the graph? Let's go back to that simple one. Let's start with this. We saw that the only graph consistent with this is the complete graph. Can I add in any other terms without changing the graph? Yes, I could add in the first order terms. Therefore, this is a non-graphical loglinear model. What it means is it's not the largest loglinear model consistent with the graph. That means it has other constraints in there, like that the beta 1 is 0, beta 2 is 0, some constraint on the multinomial, not reflected in the graph. On the other hand, of course, the full model is graphical. It is in this class. And if you think about it for a minute, I'll let you go away and think about this. It is a subset of the hierarchical condition. You can make up easily examples of things that are in here but not here. But once you make it graphical, it's also hierarchical. Let's do a more interesting example. To do really interesting examples, you need like 6 variables and so on, and it just pretty tedious. So we're going to stick to pretty low dimensional ones. So let's do, okay. What is the graph corresponding to this? Which edges should I put in? None, right? So, by the way, somebody asked me about marginal. So that applies, not only to conditional dependencies, but it applies to x1 and x2 are marginally independent because they're condition independent given the entropy. So everything's independent. Is this a graphical loglinear model? Yes, this is the biggest model consistent with this graph. If I try to put in a second order interaction term, I have to put an edge. So this is graphical. Graphical just means that when I'm looking at the graph corresponding to this, it's the most complete model consistent with this graph. If all you care about is the graph, in the end, in some sense you can restrict yourself to graphical models, putting other terms in, taking terms out, and so on. It all comes down to whether the graph's understanding. Is it a hierarchical model? Yes, if it's graphical, it's hierarchical. Let's put in another term. So the graph changes now, right? This is x1, x2. Is it graphical? Yes. If I put in any other second order interaction, I have to put in this. And if I put in the third order interaction, I have to put in theta. Is it hierarchical? Yes. But you can see again, if I took this out, it would no longer be either graphical or hierarchical. So sometimes when you see these definitions written out, formally they're a little bit confusing because it refers to if this index is in, and this index is contained in this index must also be 0, whatever, this one's 0, but it's just, I hope by writing it out on the board with a couple of examples, it's clear, fairly simple definition. One thing I really want to emphasize though is that the real distribution could be anything. There's nothing that says the real distribution has to be a graphical model and so on. And again, if you restrict yourself to only graphical models, it's just, in some sense, it might be simpler because then you know that the graph corresponds exactly to the model. you may be making things a little bit less parsimonious than you need to, but that's not such a big deal. Because again, suppose that it was the case that this was the correct model, except that beta 1 is 0. Well, the MLE would just be very small. And so, technically, in the hypothesis testing, maybe we can see we could eliminate it. But if for simplicity of interpretation you want to stick to graphical logarithmic models, you leave it in, it'll just be a small coefficient, that's all. So restricting yourself to graphical logarithmic models is not necessarily perfect. You just might have a few extra terms of the model that could have gotten there. So this distinction is important just because people mention it a lot, although it's not critical in some sense, because what it comes down to really is just fitting to a model and then drawing the graph. All right. And how do you fit the model? So far I've been talking as if nature has given us the true distribution, which means given us the true probability distribution and hence the true set of betas, but of course you're going to estimate them. And I don't want to talk a lot about numerical stuff. It's, as I said, it's typically so in the case with small dimensions, so if you have a lot of data, let's say d less than n. Then we use maximum likelihood, as I said, because the likelihood function you could, in principle, given a set of betas, go back and find the corresponding multinomial, and the log likelihood for a multinomial is simple. And so we could do your favorite algorithm. There's actually, so I don't even know what R uses. Is R uses iterative proportional? Yeah, so no, it does. It uses RLS. Oh, so it does like a numerical gradient? Newton-Raphson. So R uses Newton-Raphson to maximize the log likelihood. But there's probably other things you can do. The point is that you just stick in the data and you get the MLE. And as I said, if you wanted to see which edges you could remove or not remove, you could use your 705 knowledge to now take beta hat, say j minus 0 over its standard error, and do a hypothesis test. So I know we all did that 705. And this is one way of doing fitting log linear models. And in case you're, for the R fans out there, let me just say what the command is. I don't know what the MATLAB command is, but in R you say, actually in R there are several ways to do it. The way I do it, I don't know if this is the best one, is I use this function called GLM, which means generalized linear model, and you just regress the counts. So remember, let's go back to you reduce the data. There's actually different ways you can actually call this. The easiest way is you put these counts in. How many people are in this category, this category, this category, for example. And you just say twiddle, and I think if you say, I believe it's good enough. If I put in the highest order interaction, is that the saturated one? Yeah, so you could write it like this. You could now say x1 plus x2 plus x3 plus x1 times x2 and so on, and tell it which terms you want to fit in. But if you put the highest order interaction, it assumes you want a hierarchical model. So it's going to fit everything. So if you just put, let's suppose there's three things. This is actually going to fit beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 xt, the second order interactions and the third order interactions. This implies the full model. And here's the thing you have to say, though, to tell it, it's going to think you're doing normal linear regression unless you tell it to do a log linear model. And for certain technical reasons, the way to do that is to say Poisson. You probably are surprised to see a Poisson there. Just let's not worry about that. You'll this does what you want. This gives us the So let me just tell you, I'm just going to give you a little example so you see what, I should have posted this, just so you can see what a typical output looks like. Here's a very small example, and it's nothing you should take too seriously, but the idea here is we have 3 variables. This is data set about young newborns, and they're born with some medical problem, and the question is whether they survive or not. There's 3 variables, which was survival, and there was 2 clinics. So there was clinic 0 and 1, and it turned out there was 2 levels of care. Some of them were given ordinary care, some of them were given some sort of special emergency care. And so there's these 3 binary variables, so it just makes a good example for us. And so what you get out when you fit that in R, and I assume in other things, is you get this list of beta hats. So it gives me beta 0 hat, beta 1 hat, then it gives me the second order beta hats, then it gives me the standard errors, and then it gives me the p-values, which are precisely these tests, which I guess right here. It takes each one, this over this. This is approximately normal under the null hypothesis. It's the p-value. And so a kind of simple-minded but common way of doing this then is to say, well, I'm going to keep all the betas in the model that are significantly different than 0. And if I do that here, the model I end up getting particular, so it turns out, let me tell you which ones are not significant. The third order interaction, beta 1, 2, 3, is not significantly different from 0. So we're going to conclude that's 0. But the other one, there's a second order interaction, which is beta, let's call it the interaction of care and survival. That's also not 0, but everything else is significant. So that would imply this graph. Now this is an easy example because there are 3 variables, so that's why I picked it, but I almost hesitated to show you this example because now the danger of all this is you're going to say, well, look at that. The type of care you get and whether you survive is independent given the clinic. So it didn't matter whether you got the special care or not, it was just whether you happened to be a good clinic or the bad clinic. But why should we be careful about making interpretations like that? I mean, the conditional independence conclusion is fine in terms of approximately correct to the degree that all statistical things are sampling error, but in terms of starting to make clinical judgments from this, the problem, of course, is there's probably 10,000 other variables that we haven't recorded that are important, right? Like all these confounding variables, as we would call them. Baby's weight, socioeconomic class, what type of disease they had, 50 different blood measurements. I mean, there's a zillion other things that could be going on here that should really be part of the story. So, you know, whenever you have observational data as opposed to randomized studies, it's fine to look at this as an exploratory tool, but don't start drawing conclusions. And don't start calling CNN and saying, it doesn't matter whether we give this expensive care or not. You know, it just matters what clinic you go to. So I just bring that important note of caution there. We're using this more as a numerical example. And of course, really interesting examples, which we'll look at later. Again, you know, you don't need this analysis for 3 variables. Let's be honest, if I had 3 variables, I would just look at the counts. I don't think I'd do any statistics, okay? So it's when you have 25 variables, it starts to get more interesting. When you have, or 1,000 genes, so we'll talk about those cases. We're going to see more interesting cases when we do the non-parametric graphs, actually.
Would it also be because of multimodality in the likelihood?
Because of what?
Multimodality in the likelihood?
No, the likelihood here is concave. So those types of issues for log-linear models are non-issues. It's a nice, beautiful log. The log likelihood is beautifully concave, unique maximizer. But yeah, there's no numerical problems. So later, I'm just going to mention briefly, because I think we're going to talk about sparsity as a separate topic later on, right? So I'll just mention that if you have a high dimensional problem, maximum likelihood isn't going to work. Just like when we talk, what's the plan? Right? I'm having a whole class on what's on.
A couple classes on.
You're having a class on like high dimensional linear regression. How do you do regression when the dimension is bigger than n? The same things will apply here, so I'm kind of forward referencing a bit here. But we'll see in those cases, we'll do things like, we'll take the log likelihood function, and instead of just maximizing it when in high dimension, we need some sort of penalty, and the kind of thing we're going to be looking at in this class are things like this L1 penalty, which we touched on a bit in 701. And we'll talk about this in much greater detail in a future class. But the point is that in high dimensional cases, we need to do something different. Just plain old maximum likelihood doesn't work when you have more parameters and data points. You do some sort of sparse regression. In fact, again, for the R aficionados, you replace GLM with GLM net. Is that the right one? Yeah, that's how you do sparse high dimensional.
Is it okay to penalize all weights given that some other weights capture higher interactions?
Well, that's a good question. So the way I just wrote this down was I put this, the standard way of doing it, which is to put keyboards in it, is you don't have to do that. You could use different weights. You might want to use different weights for maybe higher order interactions. You might want to higher penalties on. So I just wrote down the kind of simplest version. Okay, so I want to move on to the normal case and then the non-parametric case. We'll finish with the multinomial case. Are there any questions about the multinomial case?
If you want to go to continuous case on discrete, that will use the same.
No, we're going to do that right now. What we're going to do, the way we get to the continuous cases, we're going to first do the normal case, then we're going to generalize from normality to more general distributions. Okay, so let's do the Gaussian case and then the non-parametric case. The Gaussian case is very simple. It's probably the simplest one, much easier than the multinomial. But also very restrictive because it makes a big assumption. So now we're leaving the discrete world, we're going to the continuous world, and we're skipping everything in between, right? Obviously you can have cases where you have some discrete and some continuous and so on, but we're just jumping right over to the continuous case. So now I have x1, xn. Again, I'm using the superscript to mean n people, but each one of these is a vector of length d. D features on n people. And the starting place for continuous graphs, now, the easiest thing always with continuous data is to assume normality first. So we'll start by assuming normality. This is the covariance matrix. And let me remind you that the inverse covariance matrix, all right, oh my God, it's sometimes called the precision matrix. Now here's a fact that you may or may not have learned in 701. I think you did, and it's proved in a note, which is simple proof. But it's a very cool thing about normals. Everything's always easy for normals, which is that xj is independent of xk, given the rest of the variables. I'm using the pairwise Markov version. If and only if the corresponding element of this is 0. So you get the inverse covariance matrix, and every 0 tells you missing edge. Is that simple or what, right? So you skip the matrix, and so you just say, oh, you think of starting with a fully connected graph, but then every time you see an entry in that matrix, which is 0, so suppose this was 0, that would say, okay, no edge between 1 and 2, and so on. So you might have edges from here to here, whatever. I'm just making up the graph here. But anytime there's a 0, you leave out the corresponding edge. So the mapping from the distribution to the graph is very simple. And this just follows from running out the normal density function using the definition of conditional density. I think you did do that in 701, yes? No, you didn't. Okay, well, all right. Now you know it. And it's a very cool, simple thing. But obviously, we don't know mu or sigma, in particular sigma that we care about here. So we have to estimate it. So again, we should distinguish the low and high dimensional cases. In the low dimensional case, so what I mean is that we have lots of data, but the dimension is fixed. The number of features per person is not some huge number. Then we can do something very simple. We can find the MLE. And what you learned in 705 is that the MLE is equivariant. That is, if I want the MLE of a function of a parameter, you just apply that function to the parameter. So the MLE of sigma inverse is just sigma hat inverse. We call it the invariance of the MLE. So I just find the MLE and I invert it. Now I have two things to deal with, which is just looking at this, I'm not going to find any zero, but I'm going to have to do a hypothesis test. I have to test these, so that's easy. I'm going to show you that in a second. But let's deal with what's the MLE. Did you do that in 701 or 705? Yes. The derivation is actually a little bit long. I even wrote it down, but probably don't want to spend time on this if you did this. And the MLE is sometimes called S. It's just the sample covariance matrix, but with an N instead of N-1, that doesn't matter. Actually, you know, it's quite a simple manipulation, but it's a little bit non-trivial just because it's a matrix and so on. But say you did see it in 701. Yes? We could post a note on it, maybe you'd rather go through it on the board if you want to do that. Does anybody want me to post the derivation? Okay. It's not hard, but I don't think it's worth spending time on it. But we can post that. But anyway, it's easy to get the MLE. There's nothing complicated or difficult here. We just compute this now. And one approach, again, to now checking if I want to set some of those equal to 0 would be to say, well, let's take the hypothesis testing approach. Let's take our estimators, coordinates of this, and do some sort of hypothesis test. And again, remember that when we did correlations, we talked about the Fisher transform, that there's a transformation of the correlation which is very close to normal. The same is true here. So, well, first of all, let me also define something for you, which is, I've been talking about the precision matrix, and the elements of that precision matrix could be any number. But when we talked about the correlation graph, the correlation was something with U minus 1 and 1, which is has a very nice interpretation. So you might wonder, is there something related to the precision matrix, which is sort of like a correlation? The answer is it's called a partial correlation. It's just a function of this. So let me just write down what it is, and then I'll give you the interpretation. So the partial correlation, let's call it So mathematically, it's this. You take the precision matrix, you take the JK element, you put a minus sign, then you divide by the corresponding diagonals. And why would we want to do this? Well, it's mainly for interpretation. So, I'm going to tell you the interpretation in a minute. There was something else I wanted to say about this. Oh, yeah. But notice that for testing purposes, right, this is 0 if and only if the corresponding element of the precision matrix is 0. So we could either check whether the precision matrix is 0 or the partial correlation is 0. Well, the reason for using partial correlations is interpretive. What is the interpretation of theta jk? It's the correlation between the two variables xj and xk after removing the effect of all the other variables. So the way to think about it is, if I take, let's write it this way. If I take, let's partition x into xj, xk, and then all the other variables. So let's call that z. So this is just, this might be the third variable, the fourth variable, and this is everything but the third and fourth variable. So I'm just going to introduce some notation here. And if I just took the correlation between xj and xk, that would be the ordinary correlation. The partial correlation says, let's remove the effect of the other variables and say, how much correlation is there between j and k after I've accounted for it, conditioned on the other variables? So formally, if I take xj minus its projection onto z, so let me call that z, and xk minus its projection, and I take the ordinary correlation, where beta, what is this? I'm doing a regression of xj onto z, and I'm minimizing it. This is just ordinary linear regression. Right, so if I take xj and regress it on here, that's just saying I'm taking xj minus beta z, I'm just doing these squares here, and I minimize that over beta. And if I take that's beta, this is just, in other words, forming the projection of xj onto the other variables. I remove the effect, and the residual that's left over is what's unaccounted for by z. And I do the same thing for this. This is the correlation between this adjusted xj and adjusted xk. It's the correlation, in other words, I'm making this too complicated. It's just the correlation between xj and xk conditional on z, once you've accounted for z. That's the difference between partial correlation and correlation. That's why we're looking at conditional dependence graphs. Did I make that really confusing? I have this feeling I made that word easier. Is that okay? It's like a correlation, but it's conditional. But the cool thing is, you don't actually have to do all this. It turns out, algebraically, you just pull out the appropriate elements of the precision matrix or rescale. This is a number between -1 and 1. It's a correlation. It's how correlated are blood pressure and weight after accounting for these 50 means. In fact, for normal models, that's equivalent to, I'm just repeating what I said up here. Xj is independent of xk given the rest, if and only if, under normality. This is not true in general. Just like, for correlation, right? We know that two variables, x and y, being independent is not the same as saying that they're uncorrelated, except in the normal case they're same here. But we're assuming normality. Yeah.
The two definitions of partial correlation, like there's the one on the right on the left, one on my left. Does that hold only for Gaussian models? Or is it
No. This part's always true, but this interpretation is only true in the Gaussian models. But the partial correlation is always satisfies that. And in fact, you can do a partial correlation graph without assuming normality. You just can't interpret it as conditional dependence.
So does that mean we expect all the diagonal elements of the precision matrix to be negative?
No.
Trying to figure the sign. But
Yeah, how about the sign? I guess it's 1. It should be 1 actually. So maybe I should have here for j not equal to k.
okay.
The other thing that's nice about this partial correlation transformation is, again, we can do Fisher's transform applies, which let me remind you what that is. It's a little bit different here. So you take zjk to be 1/2 log. Transformation is still the same. So before we use correlation, now we're using partial correlation. And under the null hypothesis that theta jk equals 0, so under the null, this is approximately normal, mean 0. The variance term is a little bit different. It's n minus d minus 1. You can see why we have to assume d is less than n. So now, this is pretty easy to program. You get your normal data, you compute the mean and the covariance. You get the MLE, which I'll write again. You just get the sample covariance matrix and invert it. You compute the partial correlations, that's just extracted from omega. You do the Fisher transform, and then you just do a bunch of normal tests. So you can reject, so you can test. Versus, you reject the null, the standardized this divided through by its standard deviation, so that means what? Multiplying by, that's bigger than, now, the typical test would be you look up, the 5% level of normal, right? So hopefully this is familiar. I'm just doing the usual normal test doing 7.5. I just take a statistic is the random variable divided by a standard deviation, which is 1 over the square root of this. However, there's one small catch here, which is multiple testing. I'm doing about order d squared tests. So remember, we should do that Bonferroni correction or some other correction. Let's say Bonferroni. So we should replace alpha. Let's say we should do this at level beta over 2 for beta is alpha divided by the number of test figures. So you can see lots of problems when d gets large. First of all, this is going to become undefined at some point. The variance is going to get very big, and also your power is going to be very low because you're going to be doing this huge adjustment. When we get into the high dimensional version in a minute, we'll actually do this a bit differently. In R, I recommend this is written by Han Liu, former student here. High-dimensional, undirected graphical estimation. It's a nice thing. You just stick in the data out, pops a bunch of graphs, and it's great. In fact, it does more than just the normal low-dimensional case that I'll explain in a minute. There's also one called the lasso. And there's another one called SIN, which only does low-dimensional cases. That was part of the first one, but to be honest, it's sort of kind of subsumed by these. And there's probably other ones. The number of our packages is like 5,000 now, so it's kind of hard to keep track of all the different ways of doing it. If you pick anything you want, like normal graphical model, there's probably 20 packages in there. And I'm sure in MATLAB, MATLAB is MATLAB packages. Although, of course, this is simple enough that you probably do this yourself tonight. So again, to forward reference a bit, what we're going to end up doing in the high dimensional case, because of that, will be, again, to replace maximum likelihood, which doesn't work. This is not going to work. where D is bigger than N. And when we get to that, you'll see again, we take the likelihood, we subtract some sort of penalty. And again, the typical penalty here would be something like, well, I think the right penalty would be this. You put an L1 penalty on the off-diagonal elements of the precision matrix. And as we'll see later on, the last arrow, things like that, these types of estimators are automatically sparse. The estimator, you don't even have to do testing. The estimator itself is going to already have zeros in it, which will tell you where the missing edges. But that's getting, that's kind of looking a little bit ahead, so you know what's going to happen in the high dimensional case. So, we now know how to do the multinomial. Fit a log in your model, draw the graph. We now know how to do the low dimensional normal, and we have a hint of the high dimensional normal. Do the MLE, bunch of hypothesis tests, draw the graph. Any questions? So there's a lot of extensions to this even in the parametric case, but you can imagine, there's millions of other parametric models and so on. And again, there's discrete and continuous and so on. So we covered the two main ones. What I want to talk about now is the next set of notes, which are some attempts to try to make graphical models a bit more non-parametric. And so before I do that, are there any questions about the model, graphical models? Everybody's okay? And we'll probably put a few examples of actually carrying this out on the next homework. And let me also say, and I'm sorry to keep saying R because that's all I know, but in R, you should also know about iGraph because iGraph is a really good package. It's also a Python version. It manipulates graphs, and in particular drawing graphs. Just drawing an undirected graph can be very difficult. iGraph has lots of ways of drawing graphs. So even if you do your stuff in R or MATLAB and you get this graph, how do you represent it? It's not trivial how to draw a good graph. So iGraph has certain things. The easiest way, by the way, I should just say, what some people do, this is what I do because I'm quite lazy, is I just put everything in a circle. And now you can always just connect everything that needs to be connected. But that might not be the best way to visualize a graph. And so some of the other things in here are, given the edges, can you find a good way to put the variables on the page so that it's really easy to look at the graph? So sort of optimal visualization of graphs is a whole research area, and this has a lot of those things built into it. It's important when you do really high dimensional graphs, and just looking at it can be a challenge. And so drawing a really bad version after doing all that hard work, and then you just see this mess can be kind of disappointing. So I'm not going to talk about visualizing the graphs, but there is software for trying to optimize them. All right, but we know how to do them, we know how to compute them, and now I want to talk about, can we make this a bit more non-parametric? So when we did regression, we learned linear regression in 701, and then we did non-parametric regression. And we did non-parametric density estimation. So is there non-parametric graphical models? There is some, and I'm going to talk about two things. Perhaps rather selfishly, it happens to be two things I worked on with John Lafferty and Con Lu. Mainly because this is what I'm most familiar with, so that's why I'm going to cover it. I want to talk about two attempts to make graphical modeling more non-parametric. And one of them is called non-paranormal. And the other one is called a non-parametric forest. what each one is trying to do here. This one is going to try to allow any possible graphical structure, but try to make the distribution a little bit more non-parametric. Doing it completely non-parametrically, especially in high dimensions, would be hard, because just estimating that distribution in high dimensions non-parametrically is hard. So this is going to be kind of partially non-parametric. But we're going to put no restriction on the graph. This is much more non-parametric, but the price we pay is we're going to restrict the graph to be a forest. A forest is just a graph with no cycles. And so a tree is a completely connected forest is a tree. And so there's trade-offs here. This is much more non-parametric, but what would happen is if your true graph looked like this, was a cycle, what this procedure is going to output is something like this. You're going to lose an edge, which in a high-dimensional case maybe is not so bad. You're getting some sort of approximation to the graph. But you're getting the advantage of doing something much more non-parametric. Whereas this one, we get all graphs, but it's not quite as non-parametric. Okay? So let's talk first about the non-paranormal. Now I have to say, we use the name non-paranormal. It's kind of a joke. It's officially called, when I tell you the real name though, I think you'll like our name better. It's officially called a semi-parametric Gaussian copula. That's what econometricians call it. That's pretty boring. I'm not going to keep saying semi-parametric Gaussian copula. So we use non-paranormal. It means kind of a, mixture of non-parametric and normal. And it's very simple. And let me say what the inspiration is. Let me go back to regression. Remember when we did non-parametric regression? In one dimension, we did something like this. Now, if x was potentially high dimensional, just taking an arbitrary function like this and trying to do penalized regression or kernel regression, there's the curse of dimensionality. And one of the things Ryan told you about was a kind of compromise, which was to do an additive model. Model y as a sum of smooth functions of the x. That's not completely non-parametric, but it's more non-parametric than just a linear model. And the idea of the non-paranormal was to try to do a similar thing. And so the way it's defined is, instead of assuming that the distribution is normal, we're going to assume that f of x is normal. But f is not some arbitrary function. It's in the spirit of this thing. It's actually a vector of functions. So what I really mean here is some function of x1 there exists some smooth function, we'll assume, of x1 and some smooth of x2, so this is normal. Now, clearly that's not completely non-parametric, not even close, but it is much more non-parametric than assuming the original data are normal. So it's exactly trying to do what this was trying to do. Instead of trying to estimate one high-dimensional function, we're estimating d one-dimensional. Okay, so we call that the non-paranormal. And the procedure is going to be pretty simple. If I can estimate these individual functions, then I just apply them to the data. Now I have data that are approximately normal, and I apply the normal ones. That's all we're doing. And that turns out to be fairly simple, because let's pick one of these variables, xj, and let's look at the CDF of xj. So fj, what's that? That's fj is, remember the CDF, just of the data variable. Let's evaluate it at some number t. So that's the probability that xj is less than or equal to t. Now, I'm going to apply f to both sides. And I forgot to mention one thing, which is, it turns out, look at this function f. I can always multiply this by a scale factor and add a constant, and call that f, right? It's this what's called identifiability. That if I added 5 to this, I could just get rid of the 5 and just call that f. In other words, it doesn't change the model at all if I just arbitrarily, I don't want to do that. If I just arbitrarily set the mean equal to 0 and actually set the diagonal of this to be Does that make sense? Let me say that again. Nothing changes if I set mu equals to 0, the diagonal to 1, because I can always, if there was a non-zero mu, I can just define that to be part of F1, just redefine F1. So there's no loss of generality. So not only by assumption, but a definition of a non-term normal, this is normal. But now I'm saying it's standard normal. So this is a standard normal. This is the problem with a standard normal. Is less than fj of t. That is, that's phi. So what we've just seen is that the marginal CDF of the j variable looks like the standard normal CDF applied to phi. If I apply phi inverse to both sides, I now have a formula for fj of t. It's phi inverse of everyone with me? We just figured out that this unknown transformation must have the form of phi inverse. This is a known thing. And this is an unknown thing. This is the marginal CDF for the random variable. But now you can see we're in good shape because we know how to estimate CDF. How do we estimate a CDF? Empirical CDF. So there's only one small minor detail, but I'll just we're going to just take where this is the empirical CDF of the j variable, but it's going to be modified slightly. Normally, it's the number of observations less than or equal to t divided by n. In fact, we're going to take a slight modification. It's the number of x, j, i's. So remember, this is the j feature, and this is the I person. And we're counting over I. How many of those are less than or equal to t? The only thing is I'm going to do a weird thing. I'm going to add a half here. And add 1 to the bottom. Asymptotically, that's a negligible change, but why did I do that? What would happen if I just used, so the usual definition would be this. What would happen, for example, at the last data point? You'd have a 1. What's phi inverse of 1? Infinity. There's sort of endpoint problems. That's just an easy way to avoid that is just to adjust this. There are other ways to do it, but this turns out to work. In fact, the notes have a much more complicated adjustment, but this actually works just fine. It's quite simple. Okay, so this is really easy now. For some reason I switched over and started calling this h hat instead of f hat. Sorry about that. This is just estimating the transformation that makes the data look normal for that variable. And now you apply your favorite normal procedure to those transformed variables. So we define, I'm just trying to see what we called it here. We give it a name. We didn't give it a name. Let's call it y, k, r, to be the transformation. And now you take the transform data, whose marginals at least should look normal now, and you apply that. You just apply either the method we just talked about, or for the high dimensional case, you apply the high dimensional version of the lasso. And that's it. It's a very simple modification. This, I think, this R program does this by default because it seems like this never hurts you. You might think if the data were already normal, maybe this extra estimation step is going to hurt you, but you never know if find an example where that actually hurts you to do this. So let me show you some pictures. There's a lot of theory in this chapter that I haven't talked about and you can ignore. It's not really important for this class. It's the idea here that we care about. First thing I want to show you, though, if you have the notes, and if you don't, I'll try to draw it on the board, is what do these non-paranormal distributions even look like? You might think it's a pretty restricted family. It's not much different from normal. Let's look at the bivariate case. In the bivariate case, I'm just taking x1 and x2 and replacing it by some smooth function of x1 and some smooth function of x2. So imagine I give you some, something, and I tell you that some smooth function of x1 and some smooth function of x2 is normal, then what must the bivariate distribution of x1 and x2 look like? I'm not really changing the joint distribution, it's just the marginals. You might think it isn't going to look much different from a normal, but you'd be wrong. Because we have some pictures here. You can get bizarre distributions even from this very limited family. So what these three pictures show you are the bivariate contours of a few examples of these non-paranormals. One of them looks like a pyramid. It's got the point. This one has 4 modes. This one has, I don't know how many modes. It's this weird multimodal thing. So what the point of these pictures is just to show you that it is not a fully non-parametric family, but it's not highly restricted either. It's kind of in between. You really can get quite a variety of different shapes of distributions. It is some sort of compromise. And a typical example of this applied to data, which should have been earlier. I'll show you an example. Actually, I'll hold off the examples until we've done the forest, because that's part of the thing. But, well, here's what we typically find. If you run this algorithm and you run the ordinary normal one, so for example, just the testing one that we did, or as I said, there's a high-dimensional version called the lasso. Typically, we find that the normal one has a lot of extra edges. It seems like if things are slightly non-normal, not always, but often, if things are slightly non-normal, the typical normal one seems to somehow, and I'm not exactly sure why, put in a lot of extra edges, whereas we tend to get a sparser graph if you do this non-paranormal. So there seems to be little harm in that. I'll show you some examples when we get further into the notes. And this is pretty easy. But there's still a big problem, which is it is still a very strong assumption on what the joint distribution is. Right? This non-paranormal family, whatever it is certainly not equal to the set of all distributions. So that's why I want to go on to the one I actually prefer, before I see this. Before I go on, any questions? Yeah. So I skipped that. There's a section in the notes where I formally define what this thing called a copula is, and I make the connection explicit between what non-paranormal and copulas. I don't think I'm going to go through it on the board because for people who aren't familiar with copulas, it's probably just all kind of become boring. If you know about copulas, or want-to-learnable copulus. It's just ways of specifying distributions through their margins, ways of specifying joint distributions through their margins. And this is clearly an example of that. And so that connection is made precise in the notes if you're interested. If you're not interested, you can just skip that. Any other questions? Yeah.
So do you worry about losing some of the like pairwise information since you're applying these functions on the margins?
No, so it turns out that in this family, these are conditional independence relations are unchanged by the function. They're preserved.
And is that that's property of the copulus?
Yeah.
Okay.
Okay, let's see if we can go more on here. So here's a really cool thing. A forest, again, is a graph with no cycles. And a fully connected forest is called a tree. We're going to now only allow the graph to be a forest. So now the way I think about this is there's no reason to think the truth is a forest. A better way to think about it is I'm going to try to find the forest that best approximates the two graphs. So that might mean omitting some edges. So we're paying a price in the expressivity of the graph. But the reward is going to be completely non-parametric. And actually, to be honest, when you get to the high-dimensional case, which is where all this is interesting, we're trying to find sparse graphs anyway. So restricting it to be a forest is probably a bonus because it's much easier, as we see, to look at a forest than to look at some arbitrary, very dense graph. So it's another way, in some sense, to make things sparse because if a forest can't be too sparse, or too dense, or it won't be a forest. So it's not necessarily even a bad thing that a forest must be a forest. And here's the key property of a forest. If I have let's say a density function for a vector x, it turns out that it's a forest if and only if I can write the density in the following very simple form. This is the marginal one-dimensional densities. Remember that a graph has a set of edges, which I'm writing here as to which things are connected to each other. So that's an edge, that's an edge. We can think of them as, 1, 2 is an edge, 2, 3 is an edge, and so on. This is going to be the product over all the pairs that are edges of the joint density. So that it's everywhere now. This is a well-known fact. This is, you can see how already it's going to simplify our lives greatly because the fascinating thing of a forest is that the whole joint density is completely determined by its one-dimensional marginals and its two-dimensional. Now this is still a little bit more complicated than it might look because this is over the edge set of the forest. This is, let's call it E of F, just to emphasize, if I drew a different forest, you'd have a different edge set. So it's not enough to determine these densities, you have to also still determine the edge set. But if I knew the edge set, the form of the density is very easy. So that assumption buys you a lot. And in particular, you can see, first of all, if I had to estimate this density given the edge set, no problem, right? All I have to do is throw in estimators. And even though this side is, technically a d-dimensional density, I never have to estimate more than a 1 or 2-dimensional density. Estimating all the 1 and 2-dimensional densities is no problem, even a large number. Everybody with me so far? I give you a forest, so I tell you the graph has no cycles, and I tell you which things are edges. 1 and 2 is an edge, 2 and 4 is not, and so on. You know you can write the density this way, and you can estimate for the next one if you have a density estimate that corresponds to that forest. What I haven't told you, though, is given a bunch of data from a distribution, how do I find the edges? How do I find the best approximating forest? Well, there's various ways to do this. There's something called Kruskall's algorithm or Chow-Liu algorithm. But I think before I do that, I want to go back to the normal case because forest. This is the instructor, yes. So, how do we find the best approximate equation? Well, we have to define what that means. So here's the way to think about this. There's a true density over this graph. We don't know it. I want to now find the best approximating forest. So one thing I might do is maximize the log likelihood over all densities. Pick the population quantity that can factorize as a forest. You can think about this as you do the Kovac-Weiler distance. Which distribution is closest in Kovac-Weiler distance to the true density, but which has a forest structure? Or that's equivalent to, because the Kovac-Weiler is a log of a ratio, and you take the log of a ratio equals the difference of logs, and there's a constant term for LA. It's equivalent to maximizing simply the expected value of log of p max subject to, so this expected value is over the true distribution. This is subject to p being forest form. But when p is a forest form, it's easy. I can write it like this. And if you plug that in there, it just ends up being minus over all edges. Xj, xk is a constant where I, let's call this I, jk, is the mutual information. This is proved in the notes, in the notes, but it's very simple. It just comes from the forest factorization. So let me try to make sure this is clear. So pick any forest you want. Suppose I gave you the true distribution for one. It may or may not have a forest representation. But I can still ask, what's the closest density among those forest structure? And if I write down the expected log likelihood, assuming this forest structure, it turns out it's minus the sum of these what are called mutual information, which is just like a non-parametric measure of correlation. It's defined this way. It's about if you take the information from theory using seams. But you can see it's a measure of correlation. These are independent. This would be log of 1, this would be 0. So it's just a non-parametric measure of correlation. And so how close the corresponding density using this forest factorization is to the true density is measured by adding up because I want to maximize this. Why do I have a minus? I think I have a, sorry, I think there's plus. Because what we want to do now, this is a well-defined problem, which is, given any forest, let's assume I knew a tree density again, for any forest, I can compute the mutual information between every pair. And now I can say for any forest, the value of the forest is just the sum of mutual informations, and I can ask, which forest maximizes that? Forget about forests now, and think back to your first algorithms class. And probably one of the things you did was, given a graph, or a tree in particular, with weights on the tree, given a bunch of nodes and weights between the nodes, how do I find the tree that maximizes the sum of the weights? Did you do that in an algorithms class? It's usually called either Kruskal's algorithm, or this particular version is sometimes called the Chow-Lu algorithm. Is that?
So we do minimal spanning tree in Kruskal's.
Exactly. So the solution is very simple. I have 1 minute left, so I'll pick this up. I guess this thing on pick it up next week. So the algorithm is very simple. I'm going to tell it to you and then I'll repeat it next week. You do the greedy algorithm. You find the two most correlated things, the things with the highest integration. So let's go like that. Now you find the next highest things and you add them in. Maybe like that. And you keep going. Now you find the next most correlated thing, but if that forms a cycle, you just throw that away. And you keep going until you're going to end up with a minimal spanning tree, a weighted minimal spanning tree. It's going to give you a full tree. And that actually maximizes this. That's the best forest, at least with respect to this measure. And so, of course, there's a complication which we don't know a piece of. Next week we'll talk about putting in estimates of that, so to estimate the mutual correlation. And so, we ran out of time. I'll finish this up quickly on Wednesday. So we'll finish this up on Monday, and then we're going to start concentration to measure. We're really switching over now from methods to doing theory. We're going to do concentration to measure, and then minimax theory, and then some optimization theory.